Hello everyone, in this video I'm going to be talking about how to predict the relative acidity when you're comparing maybe two compounds or more than two compounds based on the ARIO effect. So when I'm talking about the ARIO effects, I'm talking about as we go in an order, A stands for the atom effect, and then we have a resonance, and then we have inductive effect, and then eventually the orbital effect. And for more or less the order kind of stays that way. So you first look for the atom effect. If that doesn't help, you move on to the resonance effect. If that doesn't help, you move on to the inductive effect, and so on. So let's start out with maybe these two pairs first. So I'm comparing the ones are right next to one another. So I'm just going to go ahead and draw a line. So one of the best ways to figure out what's going to be the relative acidity is by drawing the conjugate bases of both of these guys. So I want to go ahead and draw the conjugate base of this structure here. And when I'm saying, when I'm drawing the conjugate base, all I really need to do is just get rid of that hydrogen there. So you see that hydrogen right there. I'm going to go ahead and get rid of that hydrogen as in a proton and see what's left behind. So I'm just going to go and copy this down. So that's what's left right here. And I can probably just say I lost a proton here. So that gives us this as our conjugate base. I can do something similar for the second one. So maybe I can just go and copy this down here. And now I get this as my conjugate base. Now I want to figure out of those two conjugate bases that I have just made, which one of them is more stable. So whatever conjugate base is more stable, it's going to be less basic, and the acid of that conjugate base would be more acidic. Okay, so let's start out with who is actually getting who's getting the negative charge on the conjugate base. And when I'm looking at my left one, I can clearly see that I have oxygen with a negative charge here. And on the right one, I have a sulfur with a negative charge. So since I'm getting two different atoms with a negative charge on those conjugate bases, I can rely on the atom effect, also called an element effect. So I don't really have to worry about what's going on further down in terms of resonance, inductive, and orbital. I can just answer this question based on the atom effect. Now, once you see your atoms, different atoms getting the negative charge, the first thing you want to ask yourself if those atoms are going to be in the same groups or in same period. So when I'm looking at my oxygen and my sulfur, they are actually in the same group. So when they are in the same group, the size kind of matters. So whichever is bigger in size, they will be able to handle the negative charge better. It's just that they have a better polarization because having too many electrons on a very small surface area, it's not very stable. But if you have a bigger surface area and having a bunch of electrons on it, it's that bigger surface area is more able to handle those electrons. So since sulfur is going to be bigger, so in terms of size, than oxygen, so sulfur is going to be able to handle that negative charge better. So I'm going to say that this is actually going to be a stable conjugate base. So when I'm saying stable, I'm just comparing the relative stability of those conjugate base with this one and with the left one. So relatively speaking, the conjugate base on the left side is going to be less stable. Okay, so if something is more stable, it's going to be less basic, and something that's actually less stable is going to be more basic conjugate base. But obviously, we're not really talking about the conjugate base or basicity. We are going to be looking at what's going to be the acidic strength. So whatever actually makes a stable conjugate base, the acid of that stable conjugate base is going to be more acidic. So in this particular case, we're looking at this guy to be more acidic. So that's how you're really going to be looking at it. And you can certainly, use the argument of pKa if you know the pKa's or if you're given the tables of pKa. But you know, the qualitative approach is something that you must learn because you're not going to have the pKa's on you all the time, or you're not going to have the pKa's of every single thing memorized. Okay, so that's that one. Let's move on to this next one. It's probably be better if you guys do this one and maybe pause the session and see if you get the same answer as mine. But let's just go ahead and do it, assuming that you guys already figured it out. Usually they will tell you what particular proton you are focusing on in terms of determining the relative acidity. Like in the previous case, they actually have drawn those protons out, like you got the proton here and the proton here. In this one, on the left one especially, it doesn't really say anything, but it's going to be the one that's going to be right on that methyl carbon. So this actually has three protons. I'm not going to draw all three of them. I'm only going to draw one of them so that it doesn't really look too crowded. That's the proton we're comparing with the proton that we have on this nitrogen on the right side. Okay, so again, we want to do the same thing when you're trying to determine the relative acidity. First of all, go ahead and draw the conjugate bases. So I'm going to go ahead, lose the proton here. And when I lose the proton, let's see what's left now. So we're going to have a negative charge here with a lone pair and something similar on this right side structure. And I can just copy these down. Losing the proton, I lost one of the protons there. So that means I'm going to have, this nitrogen already had a lone pair of electrons. So it's going to have now two lone pair of electrons with a formal charge of -1. Now, again, you want to ask the same question. At the conjugate base, do we have different atoms getting the negative charges? And in this case, on the left side, you certainly have a carbon here, and on the right side, you have a nitrogen. So we can certainly use an atom effect here. We don't have to worry about other things like resonance. We can just focus on the atom effect for right now. So when we're looking at the atom effect, the next question you want to ask yourself is carbon and the nitrogen are in the same group or in the same period? Well, turns out they are actually in the same period. So I can go and write that down as carbon and nitrogen are in same period. So when the things are in same periods, your electronegativity is the one that actually matters. So we want to look at the electronegativities. And between the carbon and the nitrogen, it's the nitrogen is more electronegative than the carbon. And think of this way, whichever atom is more electronegative, it can take onto that electron or it can handle that excessive pair of electron on itself better. So that's exactly what's going to happen here. Since nitrogen is more electronegative, it can handle that excessive electron pair on itself a little bit better than the carbon. So that makes this nitrogen or the conjugate base on the right side to be more stable. If this is more stable, that also means it's less basic. Okay, so that means that relatively speaking, the conjugate base on the left side, where the carbon is the one that's getting the negative charge, is actually going to be less stable. And if that's less stable, it's going to be, relatively speaking, more basic than the one on the right side, okay? And like I've said, once you figure out who is going to be more stable conjugate base, then the acid of that stable conjugate base is going to be more acidic. So at the end of the day, it's going to be this guy that's actually going to be more stable, more acidic rather, the one on the right side. So that's how you're really going to be looking at it. We can look at this next one here. So the next one, we only have one compound, all right? We're not really comparing two different compounds, but in that one compound, we have two different hydrogen atoms on two different types of nitrogens. We got one on the left nitrogen, and then we have one on the right nitrogen. So we got those two different ones that we're gonna be looking at. Okay, and again, the best way is to go ahead and draw the conjugate bases for both of them. So I'm just not really gonna draw both of those again and again. So I'll lose protons in both of those cases. And I can just go ahead and copy this. Maybe make it a little bit smaller. So if I lose the proton on the left nitrogen, then remember that left nitrogen already had a lone pair of electrons to begin with, now has two, and it gets a negative formal charge. And then I can do something similar with the right nitrogen. So I'm going to go ahead and lose one of that nitrogen's hydrogen, and now it's going to get two lone pairs on that nitrogen, where I already had one to begin with a formal charge of -1. Now you want to ask yourself, out of those two conjugate bases, or possible two conjugate bases, which one is going to be more stable? So the first question you ask yourself, who is getting the negative charge? So in the first case, on the top one, we got a negative with a -1 formal charge. And on the bottom one, we still have a nitrogen with, on the top one, we have a nitrogen with a -1 formal charge. And on the bottom one, we still have a nitrogen with a -1 formal charge. So I can't really use the atom effect here because it's the same atom doing or getting the -1 charge at the conjugate bases. So then what I need to do, maybe look at the resonances, and then you want to ask yourself, do we have any of the resonances or any of the resonances made in those conjugate bases? And turns out on the top one, that lone pair on that nitrogen is going to be in conjugation with that pi bond that's going to be on the carbonyl layer. That's an amide group. And I can actually go ahead and draw in a resonance structure where this lone pair can go down here and that can move up here. And I'm just going to copy this down. And now I'm going to erase a part of it. Now remember, the oxygen already had two lone pairs of electrons. So now I get a double bond right here. And that gets you the negative charge on that oxygen. So that's a possible resonance structure you have. But when I'm looking at the bottom one, can I have the resonance structure for the bottom lone pair on that nitrogen? And turns out we cannot, even though it kind of seems like you have a double bond right there, but it's actually too far away. That lone pair on the nitrogen is not conjugated with that pi bond because it's separated by two sigma bonds. It has to be only separated by one sigma bond like you have seen in the previous case. So for the second one, there is actually no resonance structure. But the top one obviously have a resonance, so more resonance means more stable. So since the top conjugate base is more stable, that makes this proton right here to be more acidic. Okay, so that's how you really want to be looking at it. And we can come down here, maybe do another one here, and let's see what's really going on here. I'm going to do that quickly. Like I have said, do something similar. You want to go ahead and get rid of the protons in both of those cases and see how the conjugate base looks like. Okay, so on this first one, when I go ahead and get rid of the proton, I'm gonna go ahead and get a negative charge. So this already had two lone pairs. So now it's gonna have three lone pairs on that. And I'm gonna do the same thing for the second one. Go ahead and draw the conjugate base of that. So this already had two lone pairs on that oxygen. Now I'm gonna have three on the conjugate base. And then again, you want to ask the same questions to yourself. Who is getting the negative charge? A little bit space here, maybe shorten these a little bit. Okay, so let's see, we have an oxygen with a negative charge on the left conjugate base, and the same story on the right conjugate base, we get an oxygen with a negative charge. So atom effect is out of question, or element effect is out of question. The next thing you want to ask yourself, do we have resonances made on any of those structures? And on the left one, we can clearly see that double bond right there, it's too far away. It's actually 2 sigma bonds away from that extra lone pair that we have just created on the oxygen. So there is not going to be any resonance. So no resonances for this one. But when I'm looking at the right side conjugate base, I can clearly see that that lone pair is only separated by 1 sigma bond from this pi bond. So that pi bond and that lone pair are actually going to be conjugated to one another. So I'm going to go ahead and have this resonance structure made here. I'm just going to copy this down. Remember that oxygen already had 2 lone pairs. Now it's going to have 3, and there's going to be a double bond right there. So, like I have said, if you see resonance structures, that means it's going to be more stable. So that one conjugate base on for the right acid is going to be more stable. And if that's more stable, that means it's going to be less basic. And the acid of that conjugate base is going to be more acidic. So this guy right here is going to be more acidic compared to the one that's on the left side. Okay, so that's how you're going to be looking at it. We can do something similar. Let's see for the next one. Maybe I can move this down a little bit. Okay, and the proton that we're really going to be comparing here, I'm going to make this smaller, is going to be this right here. This position has 2 protons, but I'm only going to be drawing 1 so that we're not really crowding it too much. So proton right here. Make this smaller as well. And just like I have said, go ahead and lose the proton and then see what the conjugate base is going to look like. So when I lose this proton, my conjugate base would have a negative charge right here. Okay, and when I lose the proton for this one, maybe I can draw that one down there. I'm going to have a negative charge right here. Now, okay, so in both of those cases, I got a carbon with a negative charge here on the conjugate base and a carbon with a negative charge on the second conjugate base. So your element effect is out of question. Now worry about your resonances, and I can probably start out with the second one first. And I can clearly see that that resonance, that negative charge right there is going to be is an allylic with respect to that double bond. So I can have a resonance structures made here where this can come down here and that would come out on this oxygen here. And that will give me one more resonance structure here. And that's how it's going to look like with a negative charge. I don't really have any other resonance structures on this one. With the top one, however, there is 2 possibilities, and I can probably just draw that a little bit further down. There's 2 possibilities. That's because I could technically have a resonance onto the right side, just like we have drawn for the bottom one, because that's in conjugation. And when that happens, we can see a resonance that would look like this. So that's one resonance structure. But then at the same time, we could also have this lone pair actually going onto the ring because that lone pair right here is only one bond away from the conjugated system of this ring. Or another way of saying that's also in a benzylic lone pair. So this can actually go back into the ring as well. So when this goes back into the ring, I'm going to start seeing a lot of other resonance structures as well. So is this right here. So when this comes down here, get a negative charge right there. So that's one resonance structure. And then this can just keep going now. I can have this coming down here, and that would come down here. We can have a double bond right here and a negative charge right there. So that's another resonance, and you can just keep going. I'm not really going to draw the next one, but if you can go down here, and then I can have another resonance structure. So you kind of get an idea that you'll get another resonance structure. So it turns out on the top conjugate base, you actually have more resonance structures. So more resonance structures you have, that means it's going to be more stable. More stable means it's going to be less basic, and having it more stable, the conjugate, the acid of that is going to be more acidic. So this guy is going to be relatively more acidic than the one we have on the bottom. All right, so that's how you're going to be looking at this particular one. Let's look at this comparison right here. Okay, I may not draw all the resonances on this, but just quickly do the comparison. Um, okay, so when I'm doing the conjugate basis for every one of those, how would the conjugate basis look like? I'm just going to go ahead and copy all these down here. Maybe change this to this color here. And, just get rid of the protons on every single one. And we get a negative charge. So in every one of them, it's actually the oxygen that's getting the negative charge, and there's no atom effect then. And when I'm looking at my resonances, every one of them would be capable of doing a resonance. I'm not going to draw the resonance structure, but every one of them will have one more resonance structure, so they can go down here. This pi bond will kick out onto the oxygen as a lone pair. So you have a possibility of at least one more resonance structure on every single one here. So the number of resonance structures are not really changing. So I can't really use the resonance effect here as well. So maybe I got to look at something else that would make maybe one of the conjugate bases to be more stable or less stable. So then it comes down to what else we really got on those guys. And turns out that we do have those different groups attached to them. I got a fluorine here as well, bromine here, and then there's really nothing here. And then you got a methyl group here. So now you got to worry about your electron donating, your electron withdrawing groups, or another way of saying your inductive effect. Now remember, your fluorines or your halogens are electron withdrawing groups, and electron withdrawing groups makes those conjugate bases more stable because they pull in the electrons onto themselves and stabilizing the negative charge on those oxygens in that case. Now, out of all of those, this is the one that where the off fluorine is the closest. So it's going to have the most prominent inductive effect. So this turns out is going to be the most stable conjugate base. Okay. And then when I'm looking at next on the line, I do see that the fluorine here and the bromine here, they are equally further away from those negative charges on the oxygens. But when I'm just relatively comparing the bromine and fluorine, fluorine, since it's more electronegative, it's going to have relatively more um, inductive effect. So this is going to be second most stable conjugate base, and then the bromine is going to be the third most stable. So this is second most stable conjugate base, followed by this is going to be the third most. And then it comes down to these other guys that we have here. So on those other guys, we can clearly see that, okay, well, there's really nothing on this guy, but then there's a methyl group. Now, methyl groups are actually electron donating groups, so they are actually bad for the acids, or another way of saying they will donate in the electrons onto this chain and destabilizing the negative charge on those oxygens. So I don't really want to have an electron donating group right next to it whenever you have a negative charge already on the molecule. So that is actually going to be the least stable conjugate base. Okay, and that is going to be second least stable, you can say, or fourth most stable. So if I'm um, calling these right here, so this first one with the fluorine closest is going to be the most acidic, followed by this. The next one is going to be second most acidic, and then this would be the third most acidic, and then this would be the fourth, and that would be last one. That's going to be the least acidic acid in there. So that's how you're going to be looking at an inductive effect anytime you have to look at the inductive effect on the molecules. And finally, this is maybe a relatively easier one I want to compare. And we are looking at maybe a proton on those terminal carbons here. Okay, so I want to go ahead and draw the conjugate bases for all of those. And when I'm drawing the conjugate bases for all of them, I can go ahead and get rid of those protons. And that gives me a negative charge right there, a negative charge right there, and a negative charge right there. So then you want to ask yourself, what's really the difference in the conjugate bases? And in either case, it's the carbon that's getting a negative formal charge, so atom effect is out of question. Then you want to look at the resonances. No resonances on the first one, or on the second one, and on the third one. So no resonances at all on any of those. So resonance effect is out of question. Then you look at the inductive effect. Well, in either case, you got the carbons, two carbons attached to that carbon that has a negative charge. So the number of carbons or the chain is actually the same. There is no electron withdrawing groups attached to it, so it can't use the uh, inductive effect here as well. Then it comes down to your orbital effect, which means what's really going to be the hybridization on those. And turns out this first one would be an sp3, second one is sp2, and the third one is an sp hybrid. Remember, those lone pairs are localized, so they will count in the hybridization. And also, don't forget that this actually has two more hydrogens that we don't really draw. So that's what makes it sp3, and this would have one more hydrogen here. So that's what makes it sp2. And always remember, like we have, when we're looking at sp hybrid carbons, we have 50% S and we have 50% P. When we're looking at sp2, it's 33.3% S, and then we have roughly 67%, you can say, P. And then in sp3, we have 25% S and 75% P. More P character you have, further away you're going to be from the nucleus. And the nucleus is the one that really holds on to the electrons in this particular case. You can also say that an sp hybrid carbon is going to be more electronegative, even though we're really comparing the carbons here, but an sp carbon is more electronegative than an sp2, and that's going to be more electronegative than an sp3. And the reason is the same, that we have more S character. Here, the lone pair is actually going to be the closest to nucleus. And remember, the nucleus has a positive charge, so they're going to be held on by the nucleus the strongest. So as a result, This is going to be the most stable conjugate base, and the one with sp3 hybrid is going to be your least stable conjugate base. So that leaves you with this guy to be the most acidic, and the alkane to be your least acidic. All right, so this is how you're really going to be looking at your ARIO effect. The more practice you do, the better you get. If you have any questions, feel free to leave any comments in the section below.